Welcome to Two Projects. In this video, we are going to explain the project Classification of Lung Nodules as Benign or Malignant using Image Processing and Deep Learning Techniques. Introduction. The project focuses on the development of a system for the classification of lung nodules as benign or malignant utilizing image processing and deep learning techniques. Lung nodules are small, round, or oval shaped growths in the lungs, typically measuring less than 3 centimeters in diameter, which can appear as solitary or multiple lesions on medical imaging scans such as chest x rays or computed tomography, that is, CT scans. So, in this project, we aim to address the critical need for accurate and efficient diagnosis of lung nodules, which are often indicative of lung cancer, a leading cause of cancer related deaths worldwide. Traditional methods of diagnosing lung nodules often rely on manual interpretation of radiological images, which can be time consuming, subjective, and prone to human error. Additionally, these methods may lack the sensitivity and specificity required for accurate classification, leading to misdiagnosis and delayed treatment. The significance of deep learning in this field lies in its ability to automatically learn relevant features from raw data, such as medical images, and make accurate predictions. Deep learning models can analyze vast amounts of data, capture intricate patterns, and adapt to variations in image quality and nodule characteristics, therefore enhancing the accuracy and efficiency of lung nodule classification. So, by leveraging image processing techniques and deep learning algorithms, this project aims to develop a robust and reliable system for the automated classification of lung nodules, enabling early detection and intervention, which are critical for improving patient outcomes and reducing mortality rates associated with lung cancer. Objective of the project. So, as I mentioned earlier, the primary objective of the project is to develop a robust system utilizing image processing and deep learning to accurately classify lung nodules as either benign or malignant. This involves leveraging advanced algorithms to analyze radiological images and extract relevant features crucial for precise diagnosis, thereby aiding in early detection and appropriate treatment of lung cancer. So the goal is to implement convolutional neural network, that is CNN, and CNN combined with LSTM architectures. CNNs are adept at learning spatial features from medical images, while incorporating LSTM can capture temporal dependencies in sequential data, enhancing the model's ability to analyze dynamic changes in lung nodules over time. And we aim to assess the performance of the developed models through comprehensive evaluation metrics such as accuracy, precision, recall, specificity, and sensitivity. By quantitatively measuring the model's effectiveness in correctly identifying benign and malignant nodules, we can ascertain their reliability and suitability for clinical deployment. Overall goal is to develop an automated system for lung nodule classification to benefit medical professionals, particularly radiologists and oncologists. By ensuring accurate diagnosis, this system expedites patient management, facilitates timely interventions, and ultimately improves outcomes in combating lung cancer. Additionally, earlier detection enhances treatment success and holds the potential to reduce mortality rates, benefiting patients significantly. So, requirements needed to execute this project are software requirements. Software needed is Anaconda. Primary language used is Python. Front-end framework used is Flask. Backend framework used is Jupyter Notebook. Database used is SQLite 3. And front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Now we'll discuss the working modules of law of work. So the first step is importing required packages. So the initial step involves importing essential libraries such as NumPy, Pandas, CV2, that is OpenCV, and TensorFlow's Keras module. These packages provide functionalities for data manipulation, image processing, deep learning, model development, and more, laying the foundation for subsequent tasks. The second step is importing the dataset. Here we import radiological images which serve as the dataset for training and evaluating our lung nodule classification system. These images are essential for training deep learning models to accurately distinguish between benign and malignant nodules, contributing to the effectiveness of our classification system. The third step is data pre-processing. So data pre-processing is crucial for preparing the dataset for model training. Using TensorFlow's image data generator, we perform various pre-processing steps such as rescaling, rotation, shifting, zooming, and flipping on the radiological images. These transformations enhance the model's ability to generalize and learn robust features from the data, improving its performance. Additionally, we establish a class mapping to associate numerical labels with corresponding classes such as benign, malignant, or normal. And we will divide the dataset into train and validation sets. On train set, we'll train the models, and on validation set, we'll evaluate our model's performance. The next step is training and building the models. In this step, we utilize the pre-processed data to train deep learning models, specifically CNN and CNN combined with LSTM layers. These architectures are well suited for image classification tasks and can effectively learn features from radiological images, enabling accurate classification of lung nodules as benign, malignant, or normal. So, after training the models, we evaluate their performance using various metrics such as accuracy, precision, recall, sensitivity, and specificity. These metrics provide insights into the model's effectiveness in correctly classifying lung nodules, enabling us to compare their performance and identify the most reliable approach for nodule classification. So, to provide a user friendly interface for accessing the classification system, we develop a front end using Flask, a web application framework in Python, integrated with SQLite for user sign up and sign in functionalities in this step. So, this front end allows users to interact with the system, upload radiological images, and receive classification results seamlessly. Finally, users can input radiological images into the developed system, which processes the images using the trained models to predict whether the detected lung nodules are benign, malignant, or normal. This step completes the workflow, providing users with actionable insights for early detection and intervention in lung cancer cases. Now we'll understand about the algorithms used. The first algorithm built is CNN, that is convolutional neural network. So CNNs are highly effective for image classification tasks like this project due to their ability to automatically learn relevant features from input images. CNNs consist of layers such as convolutional, pooling, and fully connected layers. Convolutional layers apply filters to input images, detecting patterns and features like edges or textures. Pooling layers then downsample the features, reducing computational complexity while retaining essential information. The hierarchical arrangement of these layers enables CNNs to learn hierarchical representations of image features, making them ideal for analyzing radiological images of lung nodules, where intricate patterns and structures are crucial for accurate classification. The next algorithm built is CNN combined with LSTM. So the CNN plus LSTM algorithm combines convolutional neural networks and long short-term memory networks to leverage the strengths of both architectures. CNNs excel at capturing spatial features from images, making them suitable for extracting meaningful patterns from radiological images of lung nodules. Meanwhile, LSTM networks are adept at modeling sequential data and capturing temporal dependencies, which is crucial for analyzing dynamic changes in lung nodules over time, as observed in sequential imaging. By integrating both architectures, the CNN plus LSTM model in this project can effectively analyze both spatial and temporal aspects of lung nodule data, thereby improving the accuracy and robustness of nodule classification, especially in scenarios where temporal information plays a significant role, such as tracking nodule progression or response to treatment. Now we'll see the comparison graphs. So this bar graph consists of subplots, each representing the accuracy, recall, precision, specificity, and sensitivity comparison graphs. So in this graph, on x-axis, I have algorithm names, and on y-axis, I have respective scores. So accuracy measures the proportion of correctly classified instances out of total instances, providing an overall assessment of model performance. Recall reflects the proportion of true positive predictions among all actual positive instances, highlighting the model's ability to detect relevant cases. Precision indicates the proportion of true positive predictions among all positive predictions, emphasizing the model's ability to avoid false positives. Specificity indicates the proportion of true negative predictions among all actual negative instances, emphasizing the model's ability to avoid false alarms and correctly classify negative cases. And sensitivity indicates the proportion of true positive predictions among all actual positive instances, synonymous with recall and critical for identifying true positive cases accurately. So, the algorithm which is best performing in all the performance metrics will be used for classifications, and we can see the CNN plus LSTM model is doing well. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is dataset folder in which I have required radiological images on which will train the models. So I have three different classes of images: benign, malignant and normal. This is models folder in which I have model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. This is static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. This is Notebook Jupyter source file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. And this is test cases folder in which I have test images on which will make the classifications. So now copy the path of the code folder from the address bar of the file Explorer. I'm copying it. Open Anaconda prompt. So now use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, and port unless configured differently. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a login link, click on it. So here we have to give our credentials, username and password and click on login button to sign in. And if we are new to the system, we have to register ourselves first. Click on sign up link. Fill in these details and click on register button to sign up. As I'm already a member, I'm clicking on the sign in link. Give the credentials here and click on login. So it has redirected us to the classification page. So now we have to upload any radiological image here, and the application will classify the lung nodule as benign or malignant or normal from the image. Click on choose file button. So these are the test cases I have. I'm selecting the first case and click on open. The image is loaded. Now click on upload button. So this is the uploaded radiological image, and here we can see the classification that is benign. So benign means the lung nodule is not cancerous but could grow slowly. So we'll try again. Click on try again link. Click on choose file button. So this time I'm selecting this image and click on open. The image is loaded. Now click on upload button. This is the uploaded radiological image, and here we can see the classification that is normal. So normal indicates that the lung nodule is not cancerous and it will not harm health. We'll try again. Click on try again button. Click on choose file button. So this time I'm selecting this one and click on open. The image is loaded. Now click on upload button. This is the uploaded image and here we can see the classification, that is malignant. So malignant means it is cancerous nodule that can spread and cause lung cancer. So early detection is important for treatment. We'll try again. Click on try again button. Click on choose file button. So this time I'm uploading this one and click on open. The image is loaded. Now click on upload button. This is the uploaded image and here we can see the classification type, that is benign. So similarly, we can upload any radiological image and can get the classifications if the lung nodule belongs to benign, malignant or normal class. Click on try again button. Choose the file. I'm selecting this one and click on open. The image is loaded. Now click on upload button. This is the uploaded image and here we can see the classification type, that is benign again. Now click on sign out. So the conclusion here is the project achieved successful development integrating image processing and deep learning techniques for accurate classification of lung nodules. This system enhances early detection and intervention, crucial for combating lung cancer mortality. The CNN plus LSTM algorithm demonstrated superior performance, outperforming CNN in all evaluated metrics, including accuracy, precision, recall, sensitivity, and specificity, thereby validating its efficacy in lung nodule classification. The deployed algorithm in the project is CNN plus LSTM model, seamlessly integrated into Flask for user interaction. Users can input radiological images and the system provides classifications as benign, malignant, or normal, facilitating efficient diagnosis and treatment planning. Medical professionals, including radiologists and oncologists, are the primary beneficiaries of this project. By providing a reliable automated system for lung nodule classification, it expedites diagnosis, improves patient outcomes, and potentially reduces mortality rates associated with lung cancer. And future scope includes enhancing the system's capabilities by incorporating advanced deep learning techniques, expanding the dataset for broader applicability, and integrating additional features such as real time monitoring and predictive analytics to further improve the effectiveness of lung nodule diagnosis and treatment. Additionally, collaboration with medical institutions for clinical validation and regulatory approval can pave the way for the widespread adoption of the developed system in healthcare settings.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.